Okay, we getting any out to the Zoom? Okay, 1, 2. Anything out to the Zoom meters? Yeah, and they hear? Can we hear them? Quick brown fox jumped over the lazy gray squirrel. How about that? Those that are old enough and did typing in school know what that is. Okay. We're good now? Yep, okay. All right. Any visitors attending this meeting? We got one? What do you mean? Everybody's doing this. What? This is my mark. Okay. There we go. Any new visitors? Well, okay. The last guy standing, he's up there, just came in. Continue standing. Give us your name and how you found the club. Okay, and how'd you find the club? All right. That's good. Do you have any equipment, or are you?
I do. I'm just kind of starting off with a job. I'm finding my way.
Well, welcome. That's 18-inch Dob. Okay, well, yeah. Little small petty thing like
one,
that.
right?
Yeah.
Hope to trade up soon.
We got you. Gonna be carrying that around in your trunk, right?
In the truck. That's exactly right.
All right. Any other new visitors? Oh, back in the back. Oh, wait a minute. Get our VP doing his jog number. That's way back there. Yeah, answer the questions.
So we heard about FWAS actually from Patrick. I'm a high school teacher, and he's done star parties out there with us.
Hold the mic closer.
Oh, I'm sorry.
There you go.
Yeah, Patrick has helped us out with star parties at Seguin High School, where I'm a physics teacher.
Great.
And so, yeah, I've been aware of you all for a few years now, and we thought we would come and say hello.
Oh, well, welcome.
Yeah. Oh, yeah, this is Oliver, my son.
Yay!
Yeah. So for equipment, we mostly use binoculars. He's got a small department store type telescope, but
yeah, he's ready to go.
Yep, he's excited.
Okay. Any other new visitors? Okay, I got a finger coming up. All right, I see it. Stand up. We're not going to shoot you or anything. I mean.
So I'm Nicholas Hefner. I heard about you guys from the TX event, TX Whiskey, but I wasn't able to make it, so I decided I would join and check it out. So, and then I have like a 20 refractor telescope.
Right. Well, welcome. Well, new visitors, if you think this club's kind of crazy or anything, you'll fit right in. So, any other new visitors? We're good?
Okay.
Okay, go for it.
I was gone for like a year and a half.
Yeah. I recognized her.
Hi, I'm Kiana Smith-Wright. Haven't seen you guys in a minute. I'm currently an undergraduate at ASU for astrophysics and data science, specifically in spectroscopy and I believe optical astronomy. Those specific ones. I came here like a year and a half ago, just looking for more astronomy, more groups, and yeah, I guess the telescope I have, it's a small 70 millimeter. Yeah.
Outstanding. Okay. Is that it? That's good. That's a good turnout. Thank y'all for coming. Next slide. Okay, please welcome our new members. Are there any new members that came tonight? Oh, I don't see any hands. Oh, one? Well, you already spoke. It's so, any on Zoom? No? Okay, next slide. Okay, here we go. Club was founded in 1949. There are 243 member accounts. Wide range of experience and everything from sun to the moons, astronomy, you name it, and this club has someone that knows how to help you with getting into that. So whatever you're interested in. Willing to help. We appreciate, you coming in and being willing to help. One of the things that I found was very helpful to me is if you don't know a whole lot, go to star parties to help. And you'll, hang around some of the guys that really know what they're doing. They'll teach you a lot just by observing. We are a nonprofit organization, so we have a lot of things going on that help a lot of organizations. Next slide. Mission, promote astronomy through outreach programs to encourage and support groups, creative observing and research among members, and to promote building of astronomy and instruments. And we do have members that actually build their own telescopes. So if you have an interest in that, we'll get that covered too. Next slide. Okay, resources, we've got member handbooks, we've got the Thompson Observatory, which is a lot of fun. Rising Star Observatory area, that's our club's own site that you can go out to, and it's dark skies. It's a portal to club telescopes, eyepieces. If you don't have equipment, we can fix you up. So you can come out to the observatory and we'll set you up. And we have an online presence, so that pretty much the club tries to cover all angles of helping somebody get into this. Next slide. This is the observatory area. It's 4 acres, and as you can see, we've got some pads. The ones with A's are leased pads. They not necessarily leased, but we do have a few lease members that in essence, if they're there, they own the pad. So watch where you set your scopes up. Because if it was me, I'd ask you to leave. No, I wouldn't. I would not ask you to leave. As long as I got a place to put my scope up, I wouldn't ask you to leave. There are members that would, though. Anyway, club pads are down on the end. Now, if nobody's there, you're welcome to use any pads there. And then we've just started RV parking, but you must sign a contract and pay $60 a year for that. Also, pets are allowed. Although I have mixed feelings on that because our neighbor has 2 large dogs, very large. They are free roaming, which means that they fetch their own food at night. So take your pet on your own risk. Our maintenance building is over in the corner, and the rest of the area says open field for setup is open for any member to set up whatever they want to set up. So that's our open field. You don't have to set up on the pads. You can set up anywhere there. Next slide, please. This is a list of our telescopes. Right now, it's not updated. We just inherited from our previous president a huge amount of scopes and materials, and we haven't got them all squared away and listed yet, but there's a lot of really great stuff that we can now provide for our members. Next scope, next slide. Okay, these are our websites for our presence online, and there's the Fort Worth Astro, and it goes on down the list. By the way, all this stuff is online for y'all to view whenever you'd like to get around to going through it. Next slide. Okay, additional info, club membership. Again, info and also the night sky. If you join the club, don't forget to go in and join night sky because we have it seems redundant, but our website is actually better access through night sky. It's got more information. That's where our calendar is and everything else for our club. Next slide. Yay. And this is our presenter for the night. I'll give you the VP to introduce him. Hello.
So, is Phil on? Dr. Metzger, are you on Zoom? Okay. All right. Well, I guess we could do what's in the sky and then do a break or something. Is it the Zoom link that ends in like 8188? Got the incorrect one. So, how do we want to play this? Let's move on.
All right, we'll let the VP handle that. Yes. Yay! Outstanding. All right, let's keep moving. I don't know where we're at. We should be coming up the raffle. So we can do the raffle, we can do the break, and then first thing, bring him back when, that'll give Bill time to get a hold of him and get him online, get things squared away. So, raffle. Who does the raffle? I do the raffle. I knew that. I was trying to pawn it off. Raffle tickets, last call. Come by. Huh? You want raffle tickets? Okay. Ah, come on, guys. No? Take them up. All right. Yes. That's a set of 3. It's gonna be a short raffle. All right, we need time for the VP, so let's see, how long can I shake this and get away with it? No, I've never done this before. There, I'm on my spot. Okay. All right, let's go with 155244. Oh, I tricked you, didn't I? I tricked our cameraman. Came to my spot and he had caught me over there. Anyway, we're good. I trust you. Just throw it there on the table. Okay. You already got, you don't want a second set? Okay. Let's go with 155253. There you go. And congratulations, we're done with the raffle. All right. So the next slide should be the break, I think. Oh, no. Hang on a second. Hang on, guys. Yes, they're looking it up. HH.71. Oh, HH 7.1. Meeting ID is 2240.
So the web link, that is correct. It's web.zoom.us with all the crazy numbers. At the very end is HH7.1.
Right, guys, we're getting there. Well, I don't know, you know. Usually I'm I've been told I'm entertaining. So I don't know about that. You have to speak to my wife. Oh, okay. Well, yeah, we can go into about anything and come back to that. Financial report by Constantine.
Thank you, Sam. Good evening, everyone. I've been told not everyone can hear me. Can y'all hear me okay? All right, terrific. Monthly report. As you can see, we've had a pretty good income as far as donations are concerned. 3525, 3,200 of that was for the mower, and another $3,000 for 2 star parties at 1687. That 3,200 for the Rising Star mower was just last month. There's been other funds that have been received since then. I think Sam may talk about those later. Next section is the Rising Star Development Fund. As you can see, it's grown quite a bit. We're at $9,600 right now. Of course, not all of that is available to us because a lot of that's going for the mower. However, please note at the bottom that we do have a loan payment coming up. And a substantial amount of that will go towards that. And we're anticipating making a payment substantially higher than the minimum required. And I'll report on that for you next month. Any questions on the financial side of things? I do have one other announcement I want to let you know about. Our meeting room here looks like may be remodeled, or portions of this building may be remodeled or updated during the summer. So obviously we're meeting here today. We'll meet here next month in May, but after that we're going to be somewhere else. And I don't know where that is yet. We're still kind of working through that. As soon as that information is available, we'll get that out through Night Sky Network so everybody has it in their personal email. So be aware of that. Yes, Matt? That was before my time. Yeah. Cy mentioned that this has happened before. Is that right, Cy? Didn't you mention that this has happened before where they were doing some remodeling? Okay. Okay. Yeah. So basically what they said was, here are your choices. They had a list of about a dozen possible locations. Sam and I went through that list and tried to identify those rooms that would accommodate us. And there was a list of 5, and we've turned those in and are waiting to hear back. Some are not as nice as this. One in particular was much bigger, and I don't know what we'd do in there. We'd get lost. Anything else for me? Well, thank you very much.
Okay, what do we got next? Executive Board update. Chris, are you online? Chris is. Okay, thanks, Stephen. Okay, we got you covered.
Chris didn't send slides for me? All right, so outreach development. All right, so for outreach development, I've been working with Chris Ashford, the director, and we have several programs that we're working through to help outreach be better. We have some reward programs, we have various ways that we're going to be trying to make outreach better. And he's got a whole presentation that was amazing that I was going to follow up with. But so stay tuned for that. I did want to make sure to recognize the hard work that our outreach is doing each and every week, multiple times a week. And that is led up by none other than our very own Patrick McMahon. Thank you very much, Patrick. You could everyone give him a round of applause. He does so much work. Thank you. And we have a number of outreach coordinators as well that we have assigned to Tandy Hills. We have added Gary Scott. Thank you, Gary. He's our Copper Breaks. Is that right? Copper Breaks, yes. He is our outreach coordinator now for that area. And each of these major areas we have coordinators with, the board has approved to buy them shirts. And I don't have all of them in, but I have a bunch, so I'll be handing those out to our outreach people tonight. So I just wanted to thank you all for all the hard work you do and for spreading knowledge and your joy and your passion for astronomy to the public.
Thank you, Kristen. As always, it's great. The outreach program. Yes, Stefan. Oh, he just popped up. Who's online? Well, let's go ahead and go with him for the break, and we'll take a break after him because we've held him up long enough. Okay. Okay. Well, I'm glad we got you online. I mean, these things happen, unfortunately. There you go. There you go, Bill. There you go, one Bill. Yeah. It'll be about 10 minutes, and then we'll get right back to you. Thank you, sir. Okay, club, let's take a 10-minute break. Or did we do 15? 10-minute break. That's what I thought. I got the number down.
check. Do I need to check on the mic?
Construction of landing pads, which will end up leading us to develop technologies for other kinds of construction as well. So people have talked about space development for decades, for a century. We've been talking about it. This is an image from Gerard K. O'Neill's concepts of having these large rotating become economically self-sustaining colonies in space, and they would be using resources from the moon to build all of this. So the problem with this concept is that it would just cost too much money. There was no business case. You would have to put hundreds or thousands of billions of dollars into this before you ever started to produce any revenue, and there's just no incentive for investors to back this, and it was too far out there for governments to back it. And so, of course, it never happened. Would have been wonderful, and maybe someday, maybe not too far in the future, it'll be viable, because if after we get robotic industry in space and we have access to billions of times greater resources, and it's largely autonomous industry in space, then we can do really great things. So we're still hoping that'll happen. Well, in the 1980s, NASA hosted a study to find out, can we break this log jam the economic logjam that was keeping us from settling space. And so they had a study about self-replicating lunar factories. And the idea was, well, if we put one factory on the moon, modest little factory, 100 tons of hardware, then it can build 3, and then each of those 3 can build 3 more. And over time, we'll end up with a gigantic industrial capability on the moon. So they studied what would it take to build this kind of a factory on the moon, little mining robots, solar panels. 80% of the mass of this can be built from the lunar soil. The other 20% of the mass would have to be brought from Earth. Since then, we've discovered there's water and carbon and nitrogen on the moon. There's not much carbon and hardly any nitrogen, but there is some. And so some circles are even more optimistic than they were back in the 1980s that we should be able to create a factory system on the moon and start to use those resources to do great things. And so I wrote a paper in 2012. I think it was published in 2012. It got the attention of the White House, and so I worked with the White House for several years to try to further this concept. Our idea was, well, instead of just building a factory and send it to the moon, let's slowly build up to the first factory. So we'll go through a bootstrapping phase. We'll put some hardware on the moon. That hardware will extract resources from the soil, and it'll build a few things. It can't build it's not self-replicating. It can't build an entire copy of itself. So in generation 2, we have to send more stuff from the Earth. But what we put together is even more capable than the first version. And so it's able to take more resources from the moon, and through a series of improving, building it up over time, we'll eventually get to a complete lunar supply chain. And then we can build anything, and then we can start to grow it into a larger factory. So we did a thorough study. We modeled the development of this industry on the moon through all these generations, and it turns out we could do this very affordably for like a third of NASA's budget over 20 to 40 years. And so it would be affordable, but it would take some time to do it. And so we were all giddy about all the great things that could happen if we follow this path. We could build space-based solar power stations. You know, they're currently not economically viable except in niche cases. But if you can build them in space with a self-replicating industry, then it would become profitable, and you could do a lot to help Earth's environment. We could move all the internet servers and high-power computing into space. You know, we were saying this back in 2010 before it became all the rage recently. We could move planetary defense into space, and build big planetary defense systems, and many other great things we could do if we had industry like that in space. And so you would be mining the moon, extracting oxygen, metals, mining the ice, getting the volatile elements, materials processing, manufacturing, construction of facilities, creating solar panels, other robotic hardware and the assembly robots, and you would use solar power to power the entire thing. It could then begin to produce benefits for humanity, and in the early stages as you're getting it started, you could use the volatiles to make rocket fuel, which could help support great science, and that would help to pay for the effort. So that was the idea, and we went through a thorough study of lunar excavation and the types of chemical reactions that would be required, metal refining, solar cell manufacturing. We used the best available data from papers that had been published, and we based this on prototypes that we had actually built at NASA, and we estimated the throughput, how fast the feedstock would be input and how fast the output in kilograms per hour would come out, and the total mass and the total power levels and the production rate. And so using that, we could estimate over time, how fast can we build up this industry on the moon to where we have 100,000 assembly robots and 60,000 tons of hardware on the moon, built up slowly over several generations of hardware. We also did a lot of hardware development work. This was a field test that we did on Mauna Kea in Hawaii, collaborating with the Canadian Space Agency. So Canadian Space Agency brought a vehicle that was dumping volcanic ash into this device that was made by NASA with Honeybee Robotics. And then this would convey the soil into this device, which used solar power, concentrated sunlight to melt the ash, and use chemical processing to extract resources. And we actually got liquid hydrogen and liquid oxygen out of the volcanic ash, and we put it over into a rocket thruster that was over under this tent, and we fired a rocket using volcanic ash, so we called it dust to thrust. And it was successful. This was back in 2012, if I remember correctly. And so we were starting to develop some of the factory hardware that could be doing industry on the moon. We did a lot of testing of reduced gravity airplane flights to make sure that all of the different systems would work in low lunar gravity, and they actually did. They worked even better than in Earth gravity. We also spent some time working on technologies to do construction of landing pads. So we took a bunch of different materials, including some simulated lunar soil that we sintered, and we bolted it down onto a launch pad, and we flew a big rocket over it. This was in the Mojave Desert. We also looked at 3D printing using an infrared laser. So we built an igloo out of lunar soil, melting the soil, letting it harden. So these were just early prototype efforts, testing out the concepts. I'm just running through a lot of examples in the preliminary before I get into the main part of the talk, in case you're wondering where this is going. We also did a lot of work on developing mining robots. This is still going on. We have a student-led competition. Every year we get 50 college teams from around the country. They build their robots and they bring them to the Kennedy Space Center, and they test who can mine the most lunar soil the fastest. And we give them points for mitigating the dust and for being low mass and for being low energy. So we're trying to drive the engineering direction to be realistic for the moon. And so we made a lot of progress. Now, why would we want to do this mining? What is the economic motivation for doing this? We tried to convince the government to bootstrap this industry, and I worked with the White House for several years. And the conclusion of that effort was, well, we still can't convince Congress to pay for it, and it's too big of an ask for commercial investors. So it's just still not happening. So since then, we've been looking for commercial opportunities that could help get industry started in space so that we can begin to go forward into these great plans. And the thing that caught most people's attention was the idea of making rocket fuel on the moon. So for decades, we've been talking about the fact that there are these permanently shadowed craters at the polar regions of the moon. This is the average sunlight for an entire year. And you can see it's very bright around the craters at the South Pole, but there's no sunlight all year long down in these craters. And the temperature in the craters is around 30 Kelvin, 30 degrees above absolute zero, extremely cold. And any water molecules that wander in there will have a dwell time in the billions of years. And so we expect it to be building up over geological timescales. We have done mapping and calculations of the thermal stability of lunar ice. So this is a map of how deep you have to dig down to get to stable ice. And you can see in some of these areas, not even in the permanently shadowed craters, you only need to dig down a few centimeters, maybe 10 centimeters or 20 centimeters to get to ice, presuming that there is ice. Or if you go down in the permanently shadowed craters, the ice should be stable even at the surface. So then we started looking for the ice to see if there is an economic opportunity, and looking at epithermal neutrons scattered by cosmic radiation off the moon. These were observed in orbit by a spacecraft. By looking at the velocities of the neutrons that are being kicked off of the moon, we can find out what fraction of those neutrons collided with protons on their way out. And because you get efficient momentum transfer in a neutron-proton collision, and you don't get efficient momentum transfer or energy transfer with collisions with heavier elements. And so by looking at the slowed down neutrons, we get a measurement of how much hydrogen is in the soil. And sure enough, in the polar regions, this is the South Pole, and I think, oh, this is the North Pole, and this is the South Pole. There is a lot of hydrogen which doesn't exist elsewhere on the moon. So then in 2009, we crashed the L-Cross spacecraft into Cabeus crater, one of those dark permanently shadowed craters. And we had 2 spacecraft watching. The impact blew out a big ejecta blanket of soil, and they looked at starlight passing through the ejecta blanket to look for absorption lines to detect what was contained in the soil. And there was a diagnostic dip in the spectrum that indicates there is water ice and that it's crystalline water ice. By looking at the size of the dip in the absorption spectrum, they measured that there was between 4 and 6 metric tons of material ejected, and about 20% of the mass was ice, 20% by weight. But it wasn't just water ice. There was methane, ammonia, carbon dioxide, carbon monoxide, and other things like some heavy metals. But it was about 5% water and about actually it's the best estimate now is that it was 8.5% by mass of ice. And so it's 3.5% everything else. So the theory is that there were this is a side view inside one of the permanently shadowed craters. The theory is that in deep time, there were asteroids and comets hitting the moon, creating temporary atmospheres, which then escaped to space because the moon's gravity is insufficient to hold the atmosphere for too long. But during that time, about 10% of the atmosphere would freeze into the permanently shadowed craters. And so you would get ice at the top of the soil. But because the moon doesn't have an atmosphere to cause small rocks and meteoroids to burn up, the moon is constantly being pummeled by these impactors, which then break up the ice sheet and mix it into the soil. So the model that we have is that there's ice mixed into the soil at some weight percent. And so people have been talking about mining it. And this was a project I did a few years ago where we said, well, let's put instead of going into a deep permanently shadowed crater, we'll go into a shallow one. And this is not to scale, but driving only a few kilometers, like maybe 3 or 4 kilometers, you can go down into a shadowy region, scoop up the soil, and then we would use pneumatics, magnetics, and electrostatics to sort out the ice from the mineral grains. And then we would haul the product back out into the sunlight where we could do the cleanup, chemical cleanup and electrolysis to make rocket fuel. We did a pretty thorough study, and it looks like it could be profitable. You could make rocket fuel, and then this spacecraft could fly back and forth to Earth orbit, boosting communication satellites. And the analysis suggests that it would become profitable over some time after the technology is matured. Other people have proposed different ideas to get the ice by shining sunlight down onto tents in the permanently shadowed craters, or by using nuclear reactors to produce the energy to heat the inside of these tents. And so the tent would be heated and the ice would sublimate out of the ground, and you'll use vehicles that are just very cold to cause the vapor to refreeze into these cold traps, and then drive over to the processor and repeat the process that I described before. Clean up the ice chemically, electrolyze it, make rocket fuel, and then haul the rocket fuel out of the permanently shadowed craters to use it economically. People have been skeptical that this could be profitable. There are people that will argue you can always launch it from the Earth cheaper than you can make it in space. And so a few years ago, I did a really thorough economic analysis. And this type of graph is the summary of that study. And so this is the lunar surface, LS. This is low Earth orbit. And so this is delivering rocket fuel to different locations between the Earth and the moon in different orbits, like geostationary transfer orbit, distant retrograde orbit, geosynchronous orbit, etc., low lunar orbit. And these are years from the beginning of operation. As you operate over time, because of the learning curve and the economies of scale, you would expect it to get cheaper as you make it on the moon. And so at first, it's true, you can't outcompete the Earth. Even at low lunar orbit, it would be same cost as getting it from the Earth. But after some years of operation, it'll be cheaper to bring it from the moon all the way down to geostationary transfer orbit. And that's where you have a business case, because now you can boost communication satellites. So it looks like it would take 5 or 7 years of operation before you could start to outcompete Earth launched. And I did the modeling. This is a different way to present the results. I don't want to take the time to explain it, but these are the economic parameters on learning curve and economies of scale, and ending the economies of scale early. And I varied every economic parameter over the full range that was viable. And in every case, this curve descends, and that means the moon is getting cheaper than Earth. So at each different location, like distant retrograde, geostationary transfer orbit, even down to low Earth orbit, lunar ice becomes cheaper. So it looks like there could be a business case, but again, the problem is investment. There aren't a lot of people that want to invest in a business that takes 7 years to make a profit when it requires that much investment and it's that risky. So all the companies that want to make lunar mining a real thing are basically depending on the government agencies to fund the effort. And so therefore it's still going pretty slow. But the big thing that seems to have changed the whole economic environment of space is this talk of putting data centers into space. Ilya Sutskever was one of the founders of OpenAI, which makes ChatGPT. And he's since left the company because they've had a lot of turmoil. But he, for example, said it's pretty likely that the entire surface of the Earth will be covered with solar panels and data centers. The idea is that AI is going to keep growing better and better, and it's going to demand ever more intelligence. And so there's a lot of people thinking that there's no upper bound on the limit to intelligence. Well, I don't believe this at all, because people won't let it happen. There's no way that people are going to let the entire Earth be covered with solar panels and data centers. However, the reason I'm pointing this out is because there's this belief that AI is going to continue to grow without an upper limit. And a lot of people, a lot of thinkers have begun to talk about that. Elon Musk has been talking about, think of terms of Kardashev 2, meaning a type 2 civilization which uses all the energy that falls on the planet Earth. And he says the path becomes obvious, meaning you have to put it into space, because it would destroy the Earth if you try to build that much compute on the planet. And Jeff Bezos said we'll be able to beat the cost of terrestrial data centers in the next couple of decades. Well, I've done detailed economic modeling of this, looking at the cost of putting data centers into orbit versus building them on the Earth. And when you take into account the political pushback against building data centers, causing increasing delay, turns out the cost of delay in construction of data centers becomes the dominant cost. So a data center that could produce $20 billion in revenue per year with a 2-year delay for environmental studies and public hearings, that's $40 billion of lost revenue. And that doesn't even account for the loss of competitiveness by the company's technology program being delayed, which could, be exponentially gigantic. So everybody has been coming around to saying, yeah, we're going to put data centers in space. The former CEO of Google said within 10 years we'll be doing it. Oh, and I didn't mention, when I ran the numbers, I tried to put as much realism as I could. And looking at the cost of launch coming down, the cost of building on Earth going up due to the environmental impact and public resistance. And the models, which were based on empirical data, predict that 10 years from now, it'll be cheaper to put them in space. And that's the same number everybody else has been concluding. Everybody's saying 10 years. And the reason environmental costs of AI are rising is because a lot of people don't like AI for a lot of reasons. It makes our energy costs higher. It's using up too much water. It's stealing our jobs. AI is going to kill everybody. And the public pushback grows non-linearly with the sprawl. And so this is what's driving the economics of putting data centers in space. So when you do detailed modeling of the space economy, this is based on Cobb-Douglas economic model, which is standard economic method of modeling off-Earth industry. Looking at 13 different sectors of in-space economic activity, like space tourism and mining helium on the moon and asteroid mining for platinum. The dominant one turns out to be data centers. And if you model space industry with and without data centers in space, you find out that data centers are responsible for dragging up the entire sector. And so if data centers really do go to space, we expect it to drag up the entire space economy, creating demand for mining in space, creating demand in processing and manufacturing and construction, so that within a reasonably short time, these are millions of US dollars, within just decades, AI, if it really grows, extrapolating the current rate, then the entire space economy will equal the entire Earth economy within this century. And so this is what governments and businesses are looking at as the potential, what's going to happen in our world. And because of this potential, there's a lot of concern about contention over the surface of the moon as countries start to scramble for resources and start to figure out how can we work together with the impact of rocket exhaust blast. I need to pause for one moment. I need to get a drink of water. Please, is that okay with you all if I just take a quick moment? Because I'm getting a little heartburn.
Of course.
I'll be right back. Okay, I'm sorry about that. Sometimes happens to me, and I didn't have a glass of water nearby. Okay, so let me shift gears now, and I'll talk about building landing pads on the moon. So because there is this thinking that the moon is going to become economically important to the world, and because nations are going to be scrambling for access to resources off of our planet, there's a lot of thinking that we're going to need to deconflict operation on the surface of the moon. And this has been my primary area of research for the past 25 years. So I've done a lot of effort studying the Apollo landing videos, looking at the blowing dust. It looks like nice little puffy dust. It's not. It's sharp abrasive glass and sharp fractured minerals traveling 3 kilometers per second in the rocket exhaust. So it's extremely damaging spray. So we've got data from Apollo 12, which landed 160 meters away from the deactivated Surveyor 3 spacecraft, which had sat on the moon for 2.5 years before the Apollo mission arrived. They cut pieces off, they brought them back to Earth. I went to Houston back around 2009, and I checked out all of the hardware. It hadn't been looked at since the 1970s, but now we have more modern equipment, and so we can do scanning electron microscope analysis and laser scans and electron dispersive spectrometry. And so we studied the sandblasting damage that happened on the Surveyor 3 because of the landing Apollo 12. And you can see that the sandblasting effect etched shadows, permanent shadows into the surfaces of the hardware, cracked up the paint. There's little tiny holes. The bottom of every one of these holes contains a sand grain. But the entire surface was pummeled by fine dust. And so it turned the Surveyor to a brown color, ruining its thermal control properties. The velocity that the ejecta goes travels globally on the moon. I don't know if you can see this circle, that's the moon. And if you simulate a 40-ton lander landing right here. This is what the spray looks like. It takes about an hour to wrap all the way around the moon, and then the spray continues to fall back in on the moon over the coming weeks. Now, by the time it travels that far, it's very widely spread, and so the damage would not be that significant. But anything in that local area within 10, 20, 30 kilometers, maybe larger, is going to be deeply damaged. So let me rerun it, and you can, whoops, you can see that it hits the surface everywhere on the moon because gravity is pulling the ejecta around the surface. Now this, NASA recently said we're not going to build the lunar gateway, at least not now, but this is the orbit that the gateway was planned to be in, and this is the circumference of the moon. And so you can see that the ejecta travels even as high as the orbit of the gateway. So the gateway traveling around the moon would be passing through the ejecta and taking some small amount of damage, even at that altitude. So let's see. So we've done a lot of work over the years, a lot of experimental work, trying to figure out the physics, the mass erosion rate, when you have supersonic rocket exhaust lifting dust off the surface, how many kilograms per second per square meter are being lifted. And we finally have solved an equation. This equation was solved just 2 years ago. And so using that equation, I compared the amount of blowing dust during the Apollo landing videos at different altitudes. And so this is a histogram of the pixel brightnesses in a rectangular area in the center of this image. And you can see when there's more dust, the histogram gets narrower and it shifts to the right, meaning the overall image is getting brighter. And so we used that as a proxy metric for the amount of dust. We wrote the equations for a camera to calculate from the amount of dust into those brightness levels in the pixels. And so if the sun is here, the rocket is blowing down here and it's blowing the dust up. So the sunlight has to go down, travel through the dust, hit the ground, come back up through the dust a second time to the camera. So when we write all the equations of light scattering and calculate the optical density, where this is the mass erosion rate, m dot, then it turns out that the theory very well matches what we saw in the Apollo landing videos. So the black dots are the measured brightness of the image, and the red dot is the theory. Now, the theory had 3 parameters. We could only get about a 30% variation on one of those parameters, and then beyond that 30% variation, you couldn't make it fit. So we know that the theory doesn't have too much flexibility, that it is accurately matching the right shape of the curve. But we do have a lot of uncertainty because this measuring the pixel brightness is a function of the amount of surface area in the dust, which is different than the amount of mass in the dust. And the relationship of surface area to mass depends on particle sizing. And it really depends on the finest particles, particles that are smaller than 3 microns. And we don't have good data on what fraction of the soil is finer than 3 microns. And that actually produces about a factor of 10 uncertainty when we convert from pixel brightness to the mass erosion rate. So it's a huge uncertainty when we say a factor of 10. Using some of the uncertainties, not even all of them, but using like 1 standard deviation of uncertainty, this is the cumulative erosion mass as the vehicle is descending. And we can only calibrate the equations until the dust becomes opaque, and we can't calibrate it down here. So that is another source of uncertainty. So we have a lot of uncertainty. And this is the depth of the resulting crater. It's greatly exaggerated in the vertical dimension. Our best estimate is that it was 6 centimeters deep at about 1 meter from the center line of the nozzle. This is what it looks like without exaggeration. You can see it's so shallow that you couldn't visually with your eyes tell that there was a crater there. And so all the lunar hoax people claim there was no crater, it didn't land on the moon. Well, there was a crater. We can see this indications of it on the lunar surface. You just can't see the overall shape of it. However, the theory that we have matches the observations on the moon. So we think we have a pretty decent theory, although there's a huge amount of uncertainty in it. And when you look at what that sandblasting will do, we can analyze if you're a kilometer away from a piece of hardware and you land 20 or 40 times, because let's say this is a lunar outpost and you're landing repeatedly, then how much of the surface coating of your hardware gets chipped off? And we can calculate the temperature of the electronics as you degrade the thermal controls. And as the temperature goes up, we can actually calculate the mean time to failure of the electronics, and it drops to the point that the electronics will last less than a year. And so you're going to be losing very expensive hardware on the moon because of overheating, because you've sandblasted it. We've also done studies of the error rates in the data after you sandblast. You know, after you launch and land 20 times, that means 10 crew rotations at the outpost, then your comm system can't process data anymore because the error rate is too high. Equipment in orbit, orbiting the moon at low lunar orbit, gets sandblasted if it happens to be right in the spray of the dust, and we could estimate the damage to the optics of the orbiting spacecraft. It's difficult to convert this into a final engineering result because it depends on a lot of factors in your optics, but it does cause damage even at orbital altitudes. This is a picture of the recent Firefly lunar landing. And you will see the shadow of the Firefly spacecraft on the surface of the moon coming down towards us as the lander descends. And I want you to watch this shadow very closely. So here comes the shadow. And look, you're going to see a dark shadow coming up from the ground towards the lander. And that's dust blowing from the surface up to the bottom of the lander and hitting the lander because it was a multi-engine lander. And so the gas was recirculating underneath it. And I'm going to stop it right there. You can see these shadows pointing out from the lander. I think those shadows are because dust is getting blown up and then it's getting caught up and the same dust is blowing back down again, making those jets darker. So you can actually damage your own lander during landing as well. But the other thing I wanted to point out in this video, which is fascinating, two things. Let's stop it right here. You can see that the dust over the horizon is not uniform. This is a panoramic camera. And so this is forward, this is off to the right, and this is off to the left. And the reason the dust is higher and brighter in these directions is because that is the symmetry planes between the multiple engines. And so it's blowing more dust in some directions and at higher angles. And now watch as the dust clears, you'll see it'll drop down, the engine cuts off, and watch the dust. It looks like the dust is falling back to the ground, but it's not. The dust is actually going over the horizon away from us as it's clearing, and it's traveling away from us at least a kilometer per second, and the curve of gravity makes it look like it's coming down, but the dust is still actually rising as it disappears over the horizon. Okay, so bigger landers with humans are going to be a bigger problem. We don't know the final mass of the Starship, but estimates 100 to 200 tons. I'm going to pick a middle of that range and say 150 tons. That's 20 times more mass and therefore 20 times more thrust than the Apollo lunar module. Blue Origin has a large lander. It's not that large, but it's also quite a bit larger than the lunar module was. And so we expect the damage to be far worse. We could get deep cratering underneath the landers, which never occurred during the Apollo missions. Okay, so how do you mitigate it? You can place your engines higher on the lander. You can build landing pads. You can build berms. You can put curtains and other barriers around your assets. You can put coatings and harden your assets against sandblasting damage. You can try to move them out of the way or put them behind hills. And you can land farther away, but the problem with landing farther away is the time value of travel back and forth to your landing site is huge. You know, the hourly cost of having a human on the moon is ginormous. So landing farther away is extremely expensive, and it's also dangerous because it exposes the crew to more radiation as they have to travel back and forth. So the best option, most people believe, is landing pad construction and berms, as well as hardening your assets. It is going to be a geopolitical issue. I'm not going to go through any details here, but there's been significant amount of analysis of the geopolitics. There's two competing efforts in the world today. There's the Artemis Accords, led by the US. There's the International Lunar Research Station, led by China. Those are both efforts that we know as norm entrepreneurship, because nobody believes that we're going to get a new updated treaty because the world is too fractured geopolitically and too much is at stake. So we're going to be stuck with just the Outer Space Treaty, and it will be international customary law that defines things beyond that. And so norm entrepreneurship is the effort of trying to create international customary law. And that's going to involve blast safety zones around your hardware, making agreements on when do we build landing pads, when are we required to build a landing pad so that other nations can exercise the right to inspect what we're doing, which is part of the Outer Space Treaty, without sandblasting us in the process. So we've done a lot of work on how do you build landing pads on the moon. The main thinking is you're going to have an inner zone, which has to handle the high temperatures. And then there's going to be an outer zone, which is much larger, much more surface area that you have to prepare in the outer zone, but it has relaxed engineering requirements because it doesn't have to handle the high temperature. And so it could be that you build two different construction methods, inner versus outer zone, and that could provide some economic advantages. And so we've looked at the various methods of building on the moon. First of all, every method requires site preparation. You have to bulldoze it, remove boulders that are sticking up. The way you do that is you dig a hole next to the boulder and then roll the boulder into the hole and then cover it over. You have to do compaction of the surface. There's been significant progress already, but we need to have adequate AI because with a 3-second time delay to and from the moon, it's really difficult to do joystick operations of construction processes. After you've done that, there are a number of different methods to stabilize the surface. One method that's been studied quite a bit is to use microwaves to sinter the soil. This is a brick of simulated lunar soil that was subjected to microwaves, and it's hard as a rock. We tested it. I showed you a picture of that landing pad in the Mojave. It was able to survive a rocket landing on it. I'm not going to go through all the details. I actually have a patent on a way to reduce the energy requirement by about 70%. And that's by using magnets to sort the soil and then keep the magnetic fraction of the soil to microwave, because magnetic susceptibility correlates to higher microwave susceptibility. Another option is to build pavers. The benefit of pavers is that you can build them in an oven and you can control the process much better. But the problem with pavers is then you need more complex robotics. You have to have some sort of interlocking them. You have to have some method of grouting, because if you don't grout them, the gas gets driven under the launch pad and then the entire launch pad explodes. We've seen that happen twice. We saw it happen in a test in Hawaii, and we saw it happen on the first Starship launch. They cracked their flat concrete landing pad. The gas got under the pad, vaporized the groundwater, and exploded the pad. And so grouting and making it mechanically competent is a big risk for using pavers. Another method is, and this is just to show that we have a lot of experience making pavers. We've been doing bricks for thousands of years. And so we've run through calculations on how fast you can build bricks and how much energy it takes, and et cetera. Another option is to use gravel and rocks. So you can get a rock rake and just rake the rocks out of the lunar soil. And then you can build them like this, where you put the finer rocks at the bottom and coarser rocks at the top. And that way, every different rock size can't escape between the next larger size that is above it. And the gases that seep their way through the rocks are increasingly slowed down so that by the time they get to the bottom, the gases are going too slow to lift any dust out. And so this was innovated by Paul Vansusante, and we've tested it. It works, but we did get erosion. This is after we picked all the rocks out. We could see that there was erosion in the central area. And that's when we realized this is not a good approach for the central part of a landing pad, but it could work in the outer part. So you need to have some central impermeable landing pad in the center zone. But we've done a lot of analysis of how fast can you rake the rocks and how fast can you sort them into different sizes. And so we've got the economic numbers for calculating the cost of gravel landing pads. Another approach is bringing polymer from the earth. This is done here on the earth to make makeshift airfields in the deserts. And there have been several different companies that have studied it under NASA contract, including for use of making heat shields out of lunar soil. So we've taken them out to NASA Ames in the ArcJet facility, and we've simulated Mars reentry using heat shields made out of dirt. And they can handle the high temperature, they ablate well, and they're really a good building material. But you may need to have 15% of the weight in polymer. Maybe 5% is as low as possible, but it's a significant amount of the mass that you have to bring from the earth to build a polymer landing pad. So we've done the economic analysis of that as well. And when you put it all together, there's 8 combinations: sintering on the inner part, sintering on the outer part, or sintering on the inner, gravel on the outer. And then I'll just say there's 2 different methods for the interior of the landing pad. There's sintering and there's pavers. And there's 4 methods for the exterior region. That's sintering, gravel, pavers, and polymer. And so looking at all 4 methods, it takes different amounts of time to build each landing pad. Sintering interior with polymer exterior is by far the fastest. They take different amounts of energy. Pavers and sintering took the highest energy. Sintering in gravel or sintering in polymer used the least. And then the amount of mass you have to bring to the moon. So using pavers requires the least amount of mass that you have to bring, whereas sintering with polymer is the most. So we can convert all of this into one common unit. The unit is dollars, because there's a time value of money, there's a cost of producing energy on the moon, and there's a transportation and hardware manufacturing cost that can be scaled by mass. And so to do that conversion, to convert everything into dollars, we have to have some numbers like the discount rate and the cost, the duration of the program, the total cost of the program, so we can calculate the delay cost from taking too long to build the landing pad. We need to know the transportation cost to the lunar surface. And these are all things that are going to vary over time. And so non-optimized, this is the total cost of building a landing pad. It's gigantic. You know, we're talking billions of dollars, $1.5 billion up to almost $4 billion. But that's non-optimized. It turns out that if you build if you have a larger number of robots, you can build it faster, but it takes more energy. And so you're trading the delay cost for the mass and the energy cost. And it turns out there's an optimum in these equations. And so when you optimize every different landing pad construction, it's still in the billions of dollars. It's like $1 billion for the cheapest method. And the cost is dominated by delivery, that's transportation of the mass to the moon. And second of all, by the delay costs, the time that it takes to build the landing pad. And now that's for the current conditions, economic conditions. But as the transportation cost to the moon comes down, there's actually a crossover point at about $21,000 per kilogram when it's cheaper to bring polymer from the earth. So this is just to illustrate that the economic conditions are variable. And so we've looked at 4 different cases of different economic conditions, and it looks like building the landing pad right now, it's going to be in the range of about $1 billion. That's the appropriated cost, not the full cost. But once we can get and that's $1 million per kilogram to the lunar surface. Once it gets down to about $100,000 per kilogram, once Starship is flying, it'll cost more like $300 million appropriated cost to build a landing pad. That's the cost of a small planetary mission. So that's getting into the range where it seems reasonable. If we can get it even further down, which SpaceX believes they're going to do, they think they're going to get it down to, even below 10,000 per kilogram to the lunar surface, which is kind of crazy, but they believe they can do it, and I hope they do. But then the cost of building a landing pad gets in the range of $50 to $40 million per landing pad. Still a bit of money, but it's more in the range of doable. So I think I can skip over this for the sake of time. So, okay, well, that was the end of it. So you can see there's not a lot of technical details on how to do construction on the moon. That's because most of the technologies are still what we call low TRL, low technology readiness level. They're all around TRL 4. Some of them, like bulldozing and grading, are up around TRL 5. But they have to be TRL 6 before you can put them into a space mission. And by the time they're flying, they have to get up to TRL 8 and then 9. So there's still a lot of technology work. And until we do that technology work, there's a lot that we need to learn about the best method to do construction on the moon. I think the conclusion of this is that there's not one way. There's a lot of variety, just like there is on the Earth. And the details of how we do construction is going to depend on the specifics, the specific economic case when you're building, the specific application that you're building for. But it's going to take a lot of work. There are a number of companies working on it. And I really do believe that we're going to see a lot of effort on the moon in the next 10 years. SpaceX wants to have a self-replicating factory on the moon in 10 to 13 years. I don't think it'll happen that soon. That's kind of optimistic, but that just gives us a sense of the timescale that we're talking about. Okay, so I thank you for having me, and I'll be happy to answer questions.
Dr. Metzger, first of all, I have a question for Dr. Metzger. First of all, excellent presentation, very informative. My question deals somewhat with the geopolitical issues that you raised briefly. Given the long-standing concern first brought up by General Boucher that the moon would become the ultimate military high ground, and the fact that we do have an outer space treaty that says we cannot exclude other nations from using lunar infrastructure that we build, right? Because there's no ability to say, this is ours, you can't use it, right?
Yes.
So now you've got 2 sort of competing ideas here. One, that the moon could become the ultimate military high ground, and the fact that we could build these bases, right, these landing places, and we couldn't prevent a country like China or Russia from using it based on the treaties that we currently have. So what is the feeling on how we would deal with those issues here?
Yeah, that's a really important question. And I can just tell you, you phrased it perfectly at the end. What is the feeling? Because it's basically a feeling that you can sense talking to people, but there are no concrete answers. The feeling that I sense whenever I talk to military people is they don't want to militarize space. They don't want to open up another domain of contention. And so it's beneficial for all parties if we can avoid that. It would dilute the military's budget even further if they had to do that. And also talking about going kinetic, and like shooting weapons in space, there's no good outcome. The kinetic results in space are far worse than they are on the Earth. So just because there's no atmosphere to slow down the ejecta, and so anything you explode continues to be a problem for 100 years. So there's not a huge desire to make it become the ultimate high ground, but there is a huge desire to make it an industrial operation. And because of that, there's going to be contention. Now, I'm a big believer in preserving and maintaining the Outer Space Treaty, and everybody that I know in this field is the same. I don't know, well, no, that's not true. There are entrepreneurs who want to throw it out. They want to say we need to be able to own property on the moon, and so there are people that want to throw it out. But everybody I know in the government and everybody I know that's a legal scholar, everybody thinks that, well, the Outer Space Treaty is not perfect, but it's a strong treaty and we need to continue working within that framework. The Artemis Accords are an attempt to interpret the Outer Space Treaty and obey it. But because the Outer Space Treaty was written before we anticipated, well, first of all, we didn't understand how rocket exhaust blast is so bad on the moon. But also it was written in a day back before we thought we were going to be building factories on the moon. You know, it was, people had anticipated one day we would, but the thinking in the 1950s was, well, we don't want to hold up the treaty for that. And so the treaty doesn't discuss serious economic development on the moon. It doesn't discuss it at all. Okay, so what is our path forward? I totally believe we need to open up discussions with China right now and find compromises so that we can work together on the moon, because it's gonna become more contentious. And because the rocket exhaust blast goes tens of kilometers, very damaging, even tens of kilometers away. If you try to build a factory and then protect it from rocket exhaust blast, you would be excluding other countries from getting within that region, which is a violation of the Outer Space Treaty. It also violates the right to inspect in the Outer Space Treaty. Every country has a right to inspect what anybody else does in space to make sure that you're not weaponizing it, for example. And so we need to come to some agreements. How can we protect hardware from being ruined, but at the same time not violate the intent of the Outer Space Treaty in terms of denying access or denying the right to inspect? So I think we can manage it, but it's going to involve building landing pads so that we can enable access without the blast creating big keep out zones. And it's going to require countries agreeing to harden their assets to withstand the blast. And so you're going to be causing yourself, you're going to be building hardware more expensively in order to enable your adversaries to land near you. So you're not naturally motivated to do that, but we need to come to agreement to do that in order to deconflict the moon. So I think that these issues are going to come to a head really quickly. In fact, I know the guy who just got appointed to be in charge of that question at the State Department, Greg Autry. He's going to the State Department and it's going to be working on that exact topic. So anyways, it's going to be a process to figure it out.
We could all just get along, right?
Well, it's going to be challenging, I'm afraid. But I mean, I'm honestly kind of optimistic. I hope that the differences between China and the US will be lessened over time. I think AI is going to make it more difficult to control information inside China. And I think AI's I think for worse, is going to make the US more like China with surveillance, becoming more deeply involved in surveillance because of the AI being everywhere. But I think the differences between China and the US may actually become smaller than our common concerns about AI. And so I'm kind of hoping that those differences will not prevent us from working together in the future. In fact, I'm currently learning Mandarin because I'm expecting we're going to have to be having discussions over these blast effects And since that's my main area of research, I'm hoping we get started talking with China really soon.
Okay, I have a question for you, sir. I find the
Yes.
landing pad discussion fascinating. Number one, is the ejecta primarily going out horizontally?
It is. Now, this picture here shows it. This picture was drawn by an artist. His name is slipping my mind. Rollins, Pat Rollins. He's a famous space artist. And when I was at NASA, we commissioned him to do this painting. And so I gave him the input on how to make the ejecta look. And so it's about a 3-degree angle above the horizontal. We measured that in the Apollo landings because you can see the shadow of the lunar module cast onto the dust. And by looking at the elongation of the shadows, you can actually measure the angle that the dust is blowing up. And it was a 3-degree angle on 2 to 3 degrees on all the Apollo landings, except for Apollo 15. And that's because they were landing over a broad, shallow crater that was ramping the dust up at a higher angle. But we actually measured that, and that agreed with the theory as well. So it is a very low angle that it goes shooting out.
The second question, would it make sense to try and put the landing pad in a small crater? And then you would get a natural berm.
Yes, that is an important strategy. It doesn't completely solve it because in vacuum, dust bounces. Here on the Earth, we don't think about dust bouncing because the atmospheric drag just stops it immediately. But in vacuum, you can think of the dust particles as being like marbles. You drop a marble on a terrazzo floor and it bounces. Well, dust bounces just like that. You know, there's a van der Waals force, but that's a conservative force. So it speeds up the dust as it approaches the larger particle. It'll rebound, and conservation of energy, it'll pull back away again. You do have about the coefficient of restitution for geological materials is about 80%. So the velocity, which is energy, velocity squared is energy. So the velocity is about 90% after it bounces and loses energy on the bounce. So dust particles only slow down 10% when they bounce off of larger particles. And so it's going to scatter the dust everywhere, but it will prevent that concentrated sheet from blowing straight out at your outpost. So that is a big mitigation. That's very helpful. But there's other challenges. If you're going to land in craters, then how many craters do you have? You know, if you're leaving descent stages behind, or if you want to have multiple landers at the outpost all at the same time, you know, you need to have enough craters. And also you don't want to have to drive out of a crater that's too steep or too far away from your outpost. So it does put some operational constraints, but it is an important strategy.
All right, we have a next question over here.
Hi, Dr. Metzger. It's a very fascinating presentation. I think you had us all pretty much on the edge of our seats. The question I had was, in the processing of the material, have y'all figured about how much, say, per metric ton would be unusable waste?
Okay, so you mean for the industry,
Yes.
for just utilizing it for general industry or for construction?
For construction.
Okay, yeah, so for construction, you know, there's been so little work, really. You know, it's all aerospace engineers and planetary scientists. We don't have building contractors yet actually bringing it to market. And so there's a lot we still have to learn about the best way to build using this material. So I wouldn't want to pretend like we really know the answer to that, but I can just give you some general thoughts about it. So lunar soil is about 20% of the mass is finer than 10 or 20 microns, which is very, very fine. And the very fine particles are actually more magnetic and more absorptive of microwaves. and then there's larger particles, there's gravel, and there's rocks mixed throughout the soil. So there might be a size distribution issue, like if you're doing a construction method that requires pouring the soil, it's really hard to pour the fine dust because it's so cohesive, it doesn't pour. In lunar gravity, if you try to pour it through a 2-inch opening, it won't go through. It'll just hang in that 2-inch opening. And so it's really hard to make it flow. If you want it to be more flowable, you got to sort out the fine dust. I was doing magnetic beneficiation, and we were splitting it about 30-70. So about 30% of the mass was more magnetic and 70% was less magnetic. You could split that mass anywhere you want. It just depends on how magnetic you want the magnetic fraction to be. It also depends on the mineralogy of the soil, and there are different mineralogies on the moon. But I was splitting it 30-70, and then the idea is you put the 70% that's not magnetic down first, and you put the 30% that is magnetic on top of it. That way, when it absorbs microwaves, the energy absorption stays in the top, and the soil beneath it stays cooler, and thermal conductivity is actually slower at low temperature. So that also helps to keep the heat in the top. So it vastly increases the energy efficiency of sintering the soil. So in that case, there would be no wasted material. It would all go into the final product because we had a use for both splits. I really can't say more than that. It's a complicated question.
Okay, Doctor, I think we've got time for 2 more quick questions. Here's one.
Do you have a sense of how homogeneous the soil on the moon is regionally, to where maybe one part of the lunar surface is more favorable for this kind of work than another?
Yeah, we do. We have a lot of data about that. The Apollo missions, they brought back hundreds of samples from each landing site, maybe not hundreds, but I think some of the later missions did. And then we also have a huge amount of orbital data. Some of the variation we can see on the moon is, we call it maturity. The lunar soil is created by asteroids hitting the moon and busting up the bedrock and throwing it out. When that happens, the resulting soil is very coarse and lots of gravel and rocks. But then over thousands and millions of years, micrometeoroids from space, interplanetary dust, pummels those rocks and breaks them up and chips them and makes them finer. And it not only makes it finer, but it also makes it redder, because the hydrogen in the solar wind is stealing oxygen out of the molten material. Whenever you have micrometeoroid hit, it creates a little bit of molten and vaporized material, and the hydrogen in the solar wind steals oxygen. So the material, when it re-solidifies, has little tiny bits of pure iron, chemically reduced. And that iron makes the spectrum more red. Because of that, we can tell from orbit what soil is young and what soil is old. The young soil is coarse, and the old soil is very fine. And so we call that immature soil, submature, and mature. And we have maps of the lunar surface. The immature soil is around the rims of young, large craters, and the crater rays that extend out, that's where the young soil, immature soil would be, which is coarser. But the intercrater areas tends to be more red and finer, mature soil. So that's one difference. The other difference, when you look up at the moon, you see the dark spots. The dark versus the light, those are the 2 main geological units. It's the mare, which is basaltic, like lava, and the highlands, which are feldspathic. It's feldspar type rocks, aluminum, sodium, and calcium type rocks. And so it's anorthosite. And so the the north acidic material is not very magnetic. It's good for making aluminum. It's good for making concrete because you get the calcium out of it, but it's quite a process to do that. Whereas the other material, the darker material, is better for microwaving. It's got a lot of iron, so you can make iron from it. And it's got a lot of magnesium. So that's the main geological difference. There are other regional and local differences as well. The geology of the moon is very complicated because the impacts have been constantly stirring the surface and mixing minerals all over the place.
Okay. Last question, real quick. Oh, no? Okay. All right. That was it.
Okay.
We're going with time. VP, you want to close?
Yeah, thank you so much. It's just like a different topic, you know? It's fascinating. I love it. So thank you for taking your time and sharing your insights with us. Really appreciate it.
You're okay, lights, Bill?
That was cool.
Or no.
Where are we in the whole?
Where are we? Are we at his section? Yeah, let's go ahead and do what's in the sky since he's up here and the lights are out.
When do we want to do what? What? Now?
Well,
What's in the sky thing?
sure.
Anybody?
We kind of skipped it. We kind of skipped it when you were out of the room.
Hey, I'm here. I got the mic, so let's do the what's in the sky thing. And there's the picture, right? So this is stuff going on for the next month. Next slide. Pretty cool to see that again, huh? Next slide. So bright comets this month. So 2025 R3 is turning into a bit of a rock star, and from what I understand, in other parts of the world where it's not Venus-like, they can actually see it. So right on for the rest of the world that doesn't have yucky skies. But apparently it's got like an incredible tail, and I think it's a morning comet right now. It's in Pisces. It's getting brighter, magnitude 7.8, and 2026 A1. That Kreutz sun grazer didn't make it, so off the list. This is a guy that I follow on AstroBin. His name is Pepe Chambo, and he does some pretty incredible work with comets. Next slide. And it's galaxy season above the layer of clouds. So this time of year, we're facing outward. The galaxy is behind us, and we're facing outwards into the openness of intergalactic space. Pictured here is Dave Cox's Markarian's chain, which we'll talk about a little later. Next slide. The Lyrids meteor shower. So on the early morning of April 23rd, we've got the second major meteor shower of the year, after the quadrantids, of course. Comet 1861 G1 is the progenitor of this particular shower. But we've got an early set. Well, we've got a set at about 3 a.m., but it's a first quarter, and yeah, it'll be a decent meteor shower if we can see the skies. I'm so bitter. I'm sorry. I'll tone it down. Next slide. Full moon. I was just streaming this whole thing with pictures of the Artemis thing. My wife and I were just like glued to the television for like all day long through the whole thing. It was fantastic. Full moon for April is on Friday the May 1st. Friday, May 1st. Next slide. Then there's the Eta Aquarids meteor shower. This one comes from 1P, which is Halley's Comet. And this one's a little bit better rate at about 30 to 60 at best. ZFR, ZHR, just to remind you, is called zenithal hourly rate. So if the radius was, the center of, the apparent center of the meteor shower was up at the zenith, that would be the rate. So it's kind of the maximum rate. Got a waning gibbous rising at 1:41 a.m., but if you can see it, it's a good one. Next slide. Jovian, hey, there's a Jovian double transit. It's Ganymede in Europa this time, and that's on May 16th. And got a nice favorable a window of both shadows on there. It's always a cool sight to see. Next slide. And then there's this shot, right? May's new moon is on Saturday, May 16th. Next slide. Okay, so I've been dreading finally getting to this constellation. It's like Sagittarius. It's like, okay, we're going to be here all night long because there's so much stuff going on in this constellation. So I tried to hit the highlights, but there's like 10,000 highlights, so, you know, get comfortable, right? So it's one of the classical constellations. Probably dates back to about 4th century BC. It was first cataloged by Ptolemy in the 2nd century in his Almagest. It's the second largest constellation footprint-wise in the sky. It's got 11 Messier objects, and it's got 18 named stars. You notice that I usually put in here that there's like, you know, whatever the count is for like how many stars have known planets. Well, I read something that said that Virgo actually has the most stars with known planets. And it was 32, and I was like, hold on a second. I thought we were in the thousands with known planets at this point. Well, that's true. I think it's something like 6,100 known planets. And I wrestled with AI to get a straight answer about that, and I was able to humiliate and correct it, which was kind of cool, so pretty good there. But yeah, I just leave it off, but apparently there's a ton of, I just don't even make that, it's an ununderstandable statistic, so I'm not gonna put it on there anymore, so forget about it. It's a lot of planets in this constellation. So it's 18 named stars. Next slide. So we get Spica. We've all heard of Spica. I wanna know, by a show of hands, how many people have heard of any of these other stars? I'm not familiar. Good on you. Good on you. Okay. That's 2 out of the whole crowd here. Now, maybe, oh my gosh. I'm like, I've never seen any of these names before. This is a thing. So, next slide. So, PSR B1257 plus 12. So this is the first star to have known exoplanets around it. So back in 1992, it was confirmed that this star actually had planets around it. And it just happens to be a pulsar, so of course it's the first pulsar to have exoplanets around it. So they were named, they actually named them in like 2015 or something like that, Poltergeist and Phobator. Scary names, but that's what's going on there. 160 times a second is how fast this pulsar has spun up, which is faster than a blender. Next slide. 3C273. Is anybody familiar with 3C273? Anybody? Not familiar? It's the first quasar that was ever discovered. Actually identified as a quasar. It's from an optical standpoint, it's the brightest quasar in the sky. It's 16 times brighter than its host galaxy. You can't see the host galaxy unless you do an occultation of the quasar, but that's where it is. Next slide. And that's it. So there you go. Now check this out. So I always usually put apparent magnitude because that's the magnitude, that's the brightness that we actually see from here. But what I did was I put the absolute magnitude. So this is an absolute magnitude of negative 26.7. So as far as what absolute magnitude says, it's a certain distance from it. So you get the degree of brightness. So it's like the brightness of the star without all of the extinction from dust between us and anything far away. So if this thing was as far away as Pollux, which is about 32 light years away, it would be as bright as the sun. So, whoa. Next slide. So there's the Virgo cluster. So as Milky Way, us and some of our friends like the Triangulum Galaxy and the Andromeda Galaxy are in the local group. So this is one of our neighboring clusters. And this, amongst other galactic clusters, make the Virgo supercluster. So that's the local structure in our neighborhood. It is probably, the Virgo cluster is estimated to have anywhere from 1,300 to 2,000 galaxies, and it spans both Virgo and Coma Berenices. So I think it was a year or two ago that I covered Coma Berenices, so there's some galaxies that were covered in that are in the Virgo cluster. Next slide. So this is, it's about 8 degrees, kind of a hard picture to find actually on the internet, but it's a large span of about 8 degrees, and it's a wonderland when you're at the eyepiece in a dark sky and you just find a galaxy and just start galaxy hopping. I did not say star hopping, I said galaxy hopping. It's a lot of fun. Next slide. So this is just the southern region of the Virgo cluster as taken by the Vera Rubin telescope. This is, I counted maybe 50 stars in this picture. The rest are galaxies, so take that. Next slide. Markarian's chain. So we mentioned that again. So they're members of the Virgo cluster, and it was actually discovered by well, it wasn't discovered, but it was named after Benjamin Markarian. He was the one who verified that the groups is moving in a common motion, so they're actually related and associated with each other. And that's it up there. Next slide. This is Jim Pott's great picture of the Markarian chain with a couple of bonus galaxies that I will cover. But it's about 1.5 degrees long, and like I said, really great for galaxy hopping. Next slide. So we're going to take a little tour of each one of these guys. You've got a elliptical galaxy with a great dust lane in it. This is Messier 84. And you've got a nice spiral that's NGC 4438. You've got another elliptical galaxy, Messier 86. These are basically galaxies that have just eaten and eaten and eaten, and they've lost all their structure. You've got NGC 4402. It's a kind of a irregular spiral, disrupted. Then you've got the EYES galaxies. This is NGC 4438 and 4435, and they call them the EYES galaxies for obvious reasons. little guy right there is NGC 4461. Little, might be a spiral, might be an elliptical. There's a couple of them like that. Same thing, this is an elliptical, 4473. It goes on and on. There's so many galaxies. 4477. So this is an elliptical that's still got a bit of a structure to it. And now, okay, so that's the end of Markarian's chain, but we got a couple of guys. Where's my laser? Where's my laser? I gotta point at things. What'd you do with it? Right here. Just like that. All right. So, anybody know what that is? You're about to find out. Yeah, you got a little galaxy over here, but you got this galaxy right here. This is a meaningful galaxy. Next slide. This guy is M87. So it's one of the most massive galaxies in the universe around us. It's called a supergiant elliptical, and it lives basically near the center of the Virgo cluster, and it contains trillions of stars. We have billions of stars around us. This is trillions of stars. Very big. Next slide. Now see, that's it right there. So next slide. So see all these little dots right here? These aren't Milky Way. Hey, go back, bro. See these are not Milky Way stars. These are globular clusters. And it's estimated to have about 12,000 globular clusters. Milky Way has a known 157. So, very large galaxy, lots of globular clusters. This is what happens when you're a galaxy that eats other galaxies. Inheritance, right? Next slide. So, there's a thing in the middle of M87 that it's a supermassive black hole, and they actually named it Powehi, which is a Hawaiian for something dark and scary sounding. And it actually creates a relativistic jet that's about 5,000 light years long. This is in the optical spectrum. This is imageable. Next slide. So if you've been living under a rock, this is the black hole that was. Hello. Oh, you died. Where's the other one?
Time's up.
Oh, thanks. Check, check.
Testing.
All right.
Testing.
Not
He just
getting
wasn't holding it right. It's still working.
Oh, not getting rid of me that easy. So yeah, this is one they imaged with Event Horizon Telescope, and yeah, look at the apparent size is, you know, what sort of size it is in our sky, and it's 0.000042 arc seconds. So this is the size of a donut if it were on the moon, or an atom at arm's length. So if you've got a telescope about the size of the Earth, you can pull off something like this. Next slide. Just numbers like that, it's just crazy. Butterfly galaxy. This Messier 104, it's an odd galaxy. So this is thought to actually be a spiral galaxy, but because it's got this like great dust laying around, it's right here. Next slide. It's got this great dust laying around it, so it's like a big donut. The thing is that it's got a larger central bulge than you see with a regular spiral galaxy. So it's resemblant of a spiral galaxy, but it's really considered to be more like an elliptical galaxy. So, fun fact about that. And this is Christopher Ashford's great picture of that. You can see the structure with the donut there, nice bulge. Next slide. So for a full listing of the 1,150 deep sky objects in this constellation, there you go, and more about that. You want to read more about M87's jet. This is a very, very cool site that talks about that. More on the discovery of the pulsar that has the first 2 exoplanets, a very interesting read here as well. Next slide. So, if we can't have skies, we can at least have rainbows, right? And so we got a Argyle Stellar Party, and we've got Whiskey Ranch Solar Party, sporting a couple of rainbows there. So keep looking up. Thank you.
Put that one there in case this dies again. Everybody close your eyes, the lights might come up. And, oh no, Mr. Bill. Oh, sun's up. Where's my dot? There it is. Okay, so, Cy. Nothing. Yay. Speed things up a little bit. Business meeting. I think we've already done that. Executive board update. Okay, we're going on. Announcements. I need to turn the lights out. I can't even see that anymore. Go to the next slide. Should highlight it. Nope. Okay. Three Rivers Ranch weekend. We got any report on that? It's pretty well set. Information, 6 cabins, going to be a lottery, I'm sure. The dining hall, there's the prices, and the club rate. This is an event that if you've got any other event for the year that you want to put on your list, this is one. I've been twice. It's a lot of fun. If the skies are clear, which we're not, it's outstanding. It really is a good trip to make. Next slide. Why aren't these highlighted? Okay, go. Yeah, it's down here somewhere. Okay, the outreach report, Patrick. Here he comes. He's got a lot. He's got his stuff together. He's already got stuff going on. I now have something I'll be able to, I never had anything to make the star parties again, or 2 other than body. I now have a 25 by 100 millimeter binocular set that I'll be bringing out there. It ought to be fun. Go ahead.
All right, thank you. So we got a number of these coming up. I'm not sure how many we're actually going to be able to see because of the clouds, but we'll give it a shot. So this Friday we have, it's actually a reschedule. This one actually may happen. It's for a gifted and talented group in South Lake. It's over in 8:30 to 9:30, so get a few scopes that would help there. Let's see. And then on May 8th, we'll have another Whiskey Ranch Solar Party. I know some of you helped out there, was successful, and there's also one in Arlington, which I'll help out with that one about the same time. And then on the 9th, we're actually going to have another star party at Fort Richardson State Park. So I was talking to them last November when I helped them out, and maybe did one in the spring, so maybe we can see some galaxies out there. So next slide. And then on the 15th, this is an annual event held in Crowley. It's Night Under the Stars. It's mostly a day event, but towards the end there, when it gets dark, we'll have some telescopes set up. People look by what we can see Venus, Jupiter for sure. Do a little solar viewing before then. And then on the 16th will be our next Dinosaur Valley Star Party, but also, as some of you have seen, Michelle has scheduled a Palapinos Mountain State Party. This is the newest state park to open, so I'm sure we can get I know we're going to get a few people to help out with that one. Those are really good skies there. And I'll update you on the e-group. Thanks.
Thanks, Patrick. Okay, John? Tandy Hill? Okay, let's move on. There's the Tandy Hill. April 25th is the date on that. This is another good one that's good to go to for for you newcomers and also for beginners like me. I'll be trying to make that one. Next slide. Okay, schedule Saturday nearest first quarter moon every month, so you can kind of pre-plan that. Location is Tandy Hill Natural Area. Let's go to, okay, young astronomers, outreach, SCI, nothing there. Okay, next. Now let's go to the next one. 1687 Foundation, Bob? Nothing to report. Okay, we're good there. That is another one when it comes up to go out with Bob's group. It's fascinating. I've been out there twice. Okay, next one. Rising Star Observing Area. Michelle, you got anything?
I think we have a video. Is that correct?
We do have a video. There's a lot of fun stories leading up to the creation of this production video. I'm going to save us time and not go into it. So, Maestro, please run the video. By the way, that's the name I used to produce videos under. Hey, Scotty, beam me down. I would like to inform the members of the club the final purchase price and delivery of the club's Kubota mower. It's been paid for and it's been delivered to the Rising Star Observing Area. Tom has given it a spin, and he says he felt like a kid on Christmas morning. He's really, really happy. By the way, this was the first time he ever drove a $8,900. That was list. As a club, we passed a total purchase price of $9,000, with $5,000 coming from club funds and $4,000 to be fundraised. The mower price changed a little bit, and I'm going to let Tom tell that story, as it's definitely his story to tell. Member contributions were $4,300. Constantine received the call, and the club was offered a $2,400 grant from North Texas Community Foundation toward the purchase price of the mower. That put us over the top. So, yeah, everything's taken care of. There are a couple other items which are badly needed, and the remaining funds will more than cover these items. One of them being the walk-behind mower. Its gearbox is broke. It's in pretty bad shape. The mower is used to mow around the bunkhouse and the areas where the Kubota can't reach. Also, one thing we've never had out there would be a string trimmer to trim around the edges of the bunkhouse and other areas such as that. I'd like to thank Tom for all the work and time he's put in to get this amazing venture of our new tractor, our new mower, keep calling it a tractor, mower, delivered to the club. Like I said, it's been an amazing adventure. So, Tom?
So, we had the vote, we had the quorum, everything passed. I was doing a little happy dance inside. I really didn't think that would happen, but it did. So then I thought, now what do I do? Well, the next day I called James Van Bieber at Kubota in Stephenville, and we worked out a deal for $400 below the list price of $8,900. We were all set up. I got a check from Constantine. We were all set up for delivery. I was driving in the evening to get some dinner for my family and I got a call from Paul Kosurik, who works for Kubota headquarters in Grapevine. And he said, Tom, I can get you a great discount. I said, what are we talking about? And he said, dealer cost. So at that point, I whipped into a parking lot and we had a discussion. I texted James and said, do not deliver the Kubota. I'll be there in the morning. And told him what was going on. He was okay with it. So the next day I drove to Stephenville and met with James, and we called Paul. And Paul walked through the whole process, what forms were needed, where to find them on the computer. And we dismissed and said, we'll get together as soon as the forms go through. About 4 or 5 days ago, I got a message from Paul that everything was ready to go, and James had the forms in Stephenville. So I drove down there, signed the sales agreement, and the price was $1,000 below what we had been quoted before at $8,900. So basically we got the Kubota for $7,900, and I drove out, it was delivered, and now we got a wonderful machine to do the 5-acre site. Again, I want to thank everybody who was involved in this, Tom Roth for his research, especially Paul for getting us that discount, and everybody that was involved in giving money to the club. Thanks again. It was a great, great pull through for everybody.
Not over yet. That's the field mowed recently. Paul? Maybe not. Okay.
Everybody needs to maybe, send him a message of how great that was. I mean, he really helped us.
I have a question.
Sure.
When the mower is not being used, is it in a secure, locked?
Oh yeah, it's locked up in a. Yeah, it's locked up, and we propose in the future, because right now there's just a couple of us that were mowing the field. We're going to have nice simple instructions, because the zero turn is easy compared to. I drove the tractor. To me, I've had a zero turn for a number of years, so for me it's very simple. But the procedure and the things that anybody can go out there with a little guidance and mow the field if you like to. I mean, these things are fun to ride, people. It's an amusement park. Yes.
There was one thing in the video I couldn't quite understand what was being said. There was something about a broken gearbox. Is that on a different mower?
Well, we have a push mower that's a power push mower, and we try to keep we're going to try to keep the zero turn out of where the mesquite trees are, which is the driveway and around the bunkhouse, because they'll puncture the tires. We looked at some airless tires, but they're extremely expensive, and for I think somewhere I heard someone say there's like a 2-year backlog on them. Yeah, 2-year wait on those. So we're going to keep the tractor away from the mesquite trees, and that push mower is used for that. Right now, we send it in for service, and they send it back to us, and it goes, you're walking along and it locks up. So you have to drag it back and then force it forward, and whatever's locking up will free itself, and then you can mow again. So that's at state right now. And with the lower price of the mower and the extra funding we've got more than enough to cover for a new Honda power mower and the trimmer, and still have additional funds left over. Yes, Tom?
So the hope is that when you guys go out to view, instead of going out like at 6 o'clock, go out at 4 o'clock and mow the field. We're going to have instructions that are very, very simple. It's a little hard to keep it going straight, as you see by the video, but to put your arms on the armrest, you can drive it straighter. It's a great piece of equipment. It's really easy to use, and you can't even go full speed on the field.
Yeah.
It's real.
Yeah, Tom says a lot of y'all have been to the field, so you kind of know it, and you saw from there, how the field looks. Our field is not smooth enough to run this thing at full speed. The little indentations that our tires make in the ground actually do leave little roughs. You try to cross those at 10 miles an hour, and it rattles your cage a little bit. So anyway, all right, next. Palo Pinto Mountain State Park. major attention. We have anyone report on that?
Well, again,
Go ahead.
again, this is where we have the new star parties. This is going to be the first one that they have in May because they just opened at the beginning of March. So she has also brought in some members of the Dallas Club. If you'll remember back before they started construction, Fort Worth and Dallas clubs held the star parties out there. So right now it looks like they've got maybe 4 scopes from the Dallas Club, and we've got almost that many scopes and binoculars coming from the Fort Worth Club. So they really do have some good skies out there to work with.
Okay, and anything else? Next slide.
Not.
Okay, very good. Yeah, right.
Real quick, I'm going to try to have an informal get-together sometime in May, just at a local park in the Tarrant County area, kind of working on that, just a social get-together, so that people can get together and just, sit around, have a good time, us to do some viewing. We need to do more of that, so we're kind of looking to do something in May. Then we're going to have a RSOA event in June.
Okay, for those online didn't hear that, Tom's putting together a club get-together, so just watch for those dates. What's a public library? I mean, I avoided books in high school. Anyway, I don't have anything for that. Website and media, George? Okay, it's still there. I guess next slide. There we go, next month. Yep, here he comes.
So we all hear about gas and rocks and stuff like that. Well, this is about her studies involving the dust that's in between the stars and, just what sort of effect it has and how they extrapolate data from the study of that dust. So that'll be a very interesting one.
Okay. Now, we have a little meeting after social club. Did we cover everything we needed to cover and talk about? Everybody's good? This is kind of a get-together down the street. It's not too far. Some of us get to go down there, beer, appetizers, some have dinner. It's a good place to go. It's fun. Okay. I guess, do I make a motion to close the meeting or second? Hey, everybody say aye. Aye. We're done.